Hi everyone, and welcome to my poster presentation on exploring the interplay between federated learning and energy systems. The poster covers our latest results at the Group for Distributed and Operating Systems at the Technische University of Berlin in carbon-efficient federated learning, as well as how to test the interaction of such distributed computing systems with the energy systems. So to reduce the footprint, the carbon footprint of federated learning, it is key to understand where clients draw their energy from. And this might be obvious for smartphones or battery-powered IoT devices, but especially in cross-silo federated learning, we often encounter very big clients, very power-hungry clients that are connected to the public electricity grid. Or maybe even clients that have access to their own on-site renewable energy generation or batteries within a microgrid. Now, one example for reducing the operational carbon emissions of FL is optimizing for renewable excess energy. And this energy occurs whenever there is more supply than immediate demand in a local energy grid. So since not all of this energy can be transferred to other regions or stored in batteries, we often encounter curtailment, meaning we have to waste this energy because we cannot match supply and demand. And this happens more and more since we deploy more and more variable renewable energy sources, like solar and wind. And for example, here we can see that in 2022, California had to curtail almost 7% of their entire solar production. So this energy is going to waste. We propose a federated learning system architecture as well as a client selection strategy, which optimizes for this renewable excess energy, as well as spare computational resources at clients. And we ask the question, how can we perform a reliable and efficient federated learning training in such a volatile and unreliable environment? For this, we had to address several challenges. For example, the issue of fairness in such a system. So how can we avoid bias towards clients that have lots of excess energy available? Or the other way around, how can we avoid that clients with very little access to excess energy are underrepresented in the final model? Zaera addresses this by dynamically adjusting the pace of training and by prioritizing clients who were so far not able to participate sufficiently. However, this is only the beginning, so there's a lot more potential for greening federated learning if we have visibility and control over the client energy systems. However, real hardware testbeds are very rare and expensive to build and maintain, so we developed a co-simulation framework called VESIM, which is able to simulate exactly that. So it combines several already existing domain-specific simulators, for instance, for solar generation, wind generation, energy storage, the grid itself, and so on, with the help of a co-simulation engine called Mosaic, which allows us to connect these simulators with real or simulated federated learning clients. And during training, the clients periodically inform the simulation about their power demand, and VESIM then simulates where this power would be coming from. And through the use of controllers, we can then simply monitor the system state and the behavior of our system, for example, by tracking carbon emissions, battery state of charge over time, etc. in a database. But we can also actively control the clients, for example, by switching some clients to power saving mode in case the simulated battery is running low. We can expose a REST interface that clients can query to get information about the state of the energy system and so on. And this bidirectional coupling is something that has not been possible with current tools. So computing system and energy system can influence each other with VESIM during experiments. We also call the software in the loop simulation. And a main goal of VESIM will be exploring this interaction. So what are meaningful and also what are safe interfaces between federated learning systems and energy systems? VESIM as well as FedZero are openly available on GitHub, so please try them out and feel free to reach out to me in case of any questions. Thank you for listening.
We introduce FedKit and demonstrates how it enables cross-platform federated learning for Android and iOS. Federated learning is a machine learning technique that enables edge devices to train a shared machine learning model while keeping training data local. In each training iteration, clients produce locally trained models. Then the server aggregates these models into a combined model. Real-world cross-platform federated learning on smartphones faces many challenges, as demonstrated by the limitations of existing systems. For example, FedML and Project Florida lacks iOS support, and Flower has not supported cross-platform aggregation, so they have not achieved cross-platform federated learning on smartphones. On the other hand, Flower and Sieve lacks machine learning operations support for production purposes. FedKit addresses these challenges by our model pipeline and custom federated learning workflow, which we demonstrate next. We demonstrate our system in action using 3 participants: a backend, an Android client, and an iOS client. We first demonstrate our cross-platform model pipeline by starting from a TensorFlow model. We convert it to TensorFlow Lite format using our TF-Lite converter, and convert it to CoreML format using CoreML tools. We then upload the models and model information to the backend. On the clients, we connect to the backend and train the model using unified training APIs. Because we carefully designed model conversion and training APIs, both clients produce model parameters in the same format, so the server can do cross-platform aggregation. While the clients are training, let's explain machine learning operations. It means that when a researcher develops a new machine learning model, they can deliver it to the client and have them start training it immediately. To demonstrate continuous model delivery, we change the MNIST model. We run through the model conversion process again, convert the TF-Lite model, record new model information, and we do the same with CoreML. Finally, we upload this model and its information to the backend, and that is the whole process to deploy a new model. Now, without even restarting, both clients prepare for the newly delivered model. This is enabled by our FL workflow. Our 2 clients just made a model request and got a new model from the backend. They then immediately enter FL server setup, and the backend spawns a new FL server as its subprocess. The clients then connect directly to this FL server for training the new model. This is our continuous FL training. The client apps did not need to be updated or even restarted to train newly deployed models. To summarize, we've highlighted our model pipeline that enabled cross-platform federated learning for Python-based model, and our federated learning workflow that enabled machine learning operations. Let's see our use case, FedCampus. It is an experiment using exercise data on university campus collected from smartwatches. We deploy an app. Within this app, we integrated FedKit to train a sleep efficiency prediction model across Android and iOS devices. And we leveraged machine learning operations with our self-hosted backend to iterate on the model in production. Finally, we're getting promising results in terms of the reducing loss. This FedCampus experiment demonstrates the real-world effectiveness of FedKit. That concludes our demonstration. Please see our GitHub repository for more information. Thank you, everyone.
Welcome to the future of sustainable mobility. Introducing Green, a platform based on federated learning, blockchain, and smart contracts. Developed by Iberia, Green is designed to securely apply artificial intelligence to Internet of Things data. Green is focused on optimizing the charging station for electric vehicles. The focus lies on improving the charging infrastructure to encourage the adoption of electric vehicles and mitigate pollution. Now, let's see how it works. Here we have a charging station. This station supplies power to electric vehicles and, at the same time, records the electricity consumption throughout the day. Through this data, the station can train its own local model to predict its future consumption. However, in a city, we face a dilemma. Each station has its own local model, but local data is not sufficient for accurate models. So, how do we solve this? The answer is collaboration. But there's a problem. Each station belongs to a different manager, and they don't want to share data. This is where Green comes in with its innovative technology. Green uses federated learning and blockchain to overcome this obstacle. Each station has its own local models. Thanks to the blockchain, we create a network to evaluate and vote the local models, ensuring we get the best possible results. Now, thanks to the federated learning, instead of sharing data, stations combine their local models to form a global model beneficial for all, and this global model is updated in each run. Additionally, this model is securely stored within the blockchain along with the smart contracts and other data. But what happens if a station tries to act maliciously in the network? It's time to dive into the training process and address all your questions. As we have already seen, the charging stations gather data on the energy demand from their customers. Each station uses this data to train and validate a local predictive model for its future energy demand. Once trained, each station shares its trained model with the rest of the network throughout peer-to-peer communication. The rest of the stations evaluate the quality of the received model with their own data. Throughout a consensus algorithm governed by the smart contract, all the nodes vote on whether to add this update to the global model. If the update is accepted, each node includes the model in its record. The locally validated models are federated to form a new, updated global model. On one hand, the local models, together with the updated global model and the smart contracts, are stored as data blocks. These blocks are permanently added to the blockchain ledger, becoming an immutable record. On the other hand, the updated global model is sent back to the charging stations after an evaluation regarding its implication in the network. Finally, the smart contract automatically executes, providing rewards or penalties to the stations that have sent the models. If their models are accepted, the station will receive better updates from the other nodes. If rejected, access to new updates will be blocked and a penalty will be imposed. Here you have the overview of the whole training process. This was just a quick overview of a fraction of green capabilities. Visit our website or contact us for more information.
Hello everybody, this is Lorenzo Carnevale, Assistant Professor at the University of Messina. Along with my colleagues, we worked on a novel federated learning framework for mobile edge devices, such as robots. This is why the Robot Operating System (ROS) is at the center of the discussion. Let's step back for understanding the context. It was 2017 when McMahon and his colleagues from the Google Incorporation released a paper discussing on a communication-efficient learning methodology based on decentralized data. Local data were trained locally on decentralized clients, and the model's weights were shared with an aggregated server, which performs averaging by using the federated averaging algorithm. Such a paradigm was therefore named federated learning. Federated learning has found applications in many domains and industrial sectors, such as smart city, healthcare, and robotics. In the latter domain, robotics, greater interest has aroused the convergence of federated learning and unmanned aerial vehicles used for the optimization of communication or resource allocations. Many federated learning frameworks have been already released, but no solution for ROS-based application have been implemented yet. Moreover, ROS2 communication is based on the Data Distribution Service, a standard for data-centric publish-subscribe. This means that no existing framework may fit as it is. As an alternative, FedROS is built on top of ROS2 for enabling federated learning on ROS-based mobile edge devices. FedROS is designed to be a platform-as-a-service cloud computing model for the submission of federated learning jobs. FedROS user implements model, optimizer, and loss function by extending abstract classes. Such files, along with hyperparameters and dataset, are organized in a YAML manifest, which becomes the input of the application. We faced two main issues. The first one is related with the ROS2 needs, that are the building in runtime of client and server packages. However, we didn't know a priori the manifest that the users submit. The second one is related with the communication system, because ROS needs to define a message format before of the building phase. We created two not self-sufficient ROS2 packages. Model, optimizer, loss function, dataset, and hyperparameters configuration files land on the packages after a composition phase. The FedROS client package has a training node, which implements the methods to train the local model, while the FedROS server package has an aggregation node, which implements the FedWG strategy. Therefore, we compose also the interface message as the programmatical extraction of layers name, number of parameters, and shape. This is an example. Finally, a Docker Compose was programmatically made for running client containers and server containers on the machine for the simulation. The experiments aim to evaluate the time performance of the FedROS client and FedROS server packages. The generation of all the files is characterized by input-output operations on disk, but in particular, the interface configuration takes more time, as the framework must analyze the structure of the neural network model to extract the layer's name, the number of parameters, and the shape. Finally, the FedROS framework fills a gap in the utilization of federated learning in mobile edge devices, for example robots. The framework has good performance and represents a benchmark by itself. In the near future, we will act for testing the client-server communication efficiency, both for the publish-subscribe model, which is already implemented, and the client-service model, also native in ROS2. This is an asynchronous communication system and promises a faster interaction. Furthermore, we would like to simulate a real scenario distributed environment, for example, a swarm of drones. These are my contacts. Feel free to keep in touch with me. And this is the bibliography used for this presentation. Have a nice day. Bye.
Hi, I'm Amândio, and this is CoLExT, Collaborative Learning Experimentation Testbed. CoLExT is developed as a collaboration between the University of Ljubljana and the KAUST University. Cross-device FL research rarely extends beyond simulated environments because of a lack of access to devices and the non-trivial nature of code deployment across a wide variety of systems with different computing architectures. But if we only stick with simulation, how do we know if the simulation is actually realistic? And how efficient are FL algorithms on real edge devices and smartphones? With the aim of answering these questions, we set out to achieve the following objectives. First, to build a research testbed that gives researchers access to these devices. Second, to make it as simple as possible to push FL research to real devices. We should be able to get standard research code and automatically push FL experiments to devices while hiding the details of their different computing environments. Third, hardware metrics should be automatically collected and easily visualized. Currently, CoLExT comprises both Android and Linux devices. We have 14 different device types that were selected to cover a wide range of performance capabilities, from low to high-end phones and single-board computers. In total, we have 48 devices. 20 are smartphones and 28 are single-board computers. Additionally, our testbed contains a workstation that acts as our FL server. We have a Monsoon high-frequency power meter to get accurate energy consumption from devices, and we connect all devices using a dedicated wired and wireless network. To interact with CoLExT, the researcher specifies a simple configuration file describing the code entry points for the client and the server, the arguments for each, and, most interestingly, which devices they want to have as clients. Custom datasets are also supported, and they can be optionally configured on the configuration file. Additionally, the researchers can annotate their Flower client and server using decorators to automatically retrieve hardware metrics from the devices. With the setup ready, the researcher can submit a job to CoLExT. CoLExT then takes care of deploying the experiment on the requested devices and collecting the logs and hardware metrics of the clients. This data can then be analyzed through a Grafana dashboard. Let's now take a look at what a real interaction with CoLExT might look like. This starts with the installation of the CoLExT Python package, and with the assuming the package is installed, let's consider a simple code example using a Flower tutorial example. So first, the user writes a configuration file with the client and the server entry points, and also, and most importantly, the desired client hardware. After that, we annotate the Flower client using our decorator, and note that the decorator does not modify the behavior of the program if the code is running outside of the CoLExT environment. And then we add a similar decorator to the Flower strategy. With everything set up, we can launch the job to CoLExT, and the launch will take care of automatically containerizing the application and deploying it to the correct devices. Once the experiment starts running, we get a link to the Grafana dashboard where we can monitor and analyze the metrics collected. To avoid waiting, here's a previous example. It contains the hardware metrics of the devices and also client and server logs to help debug applications. The dashboard, we can also isolate the data from the individual clients. CoLExT still has a long way to go, and currently we're facing a few key limitations. For one, experiments can only be deployed across a subset of single-board computers or Android devices. We can't use both at the same time. This is caused by a lack of serialization compatibility. Next, on Android devices, we're restricted to Kotlin or Java, which unfortunately cannot be directly converted from the more common FL code written in Python. This will require some manual work from the researcher. However, we have a detailed Android example template that researchers can use and minimally modify. Final limitation is that we're currently limited to TensorFlow Lite on Android due to the low machine learning framework support for machine learning training on Android. To conclude, this has been CoLExT, a collaborative learning experimentation test. To learn more about the project and get in touch, please check the CoLExT project page by scanning the QR code. Thank you for listening.